teach you how to further analyze graphs of polynomial functions. This will build off the previous lesson in which you learned some of the basics of polynomial functions as well as their end behavior. We're going to look at a few more concepts that relate to analyzing functions, specifically focusing on zeros, minimums, and maximums. So there's some key vocab you see here on the left side of the screen, and on the right side you notice I already have my graphing calculator up. We are going to use the graphing calculator to find some of these new concepts that we've talked about to some degree, but now we're going to use our graphing calculator to kind of speed up the process a little bit. So if you don't have that handy as you're watching the video here, I would recommend it so that way you can follow along and press all the buttons as needed. So some of the key vocab you see here on this initial slide. We've talked about what zeros are. They're x-intercepts of a graph. That's not anything new. And we've talked about minimums and maximums, minimum being the lowest point, maximum being the highest. One other way that we're going to rephrase the concept of minimum and the maximum is the concept of a turning point. Now, we technically saw turning points in the last unit when we graphed the parabolas. They just only had one turn, and that occurred right at the vertex. These graphs, as we kind of saw in the last lesson, these graphs will turn at multiple points because there are more x's involved. It's a higher degree and there's more moving parts. All a turning point is when the graph changes direction from increasing to decreasing or vice versa. These turning points occur at a series of minimums and maximums. Now, in some of these graphs, you might see more than one low point or more than one high point. So the phrasing that we're going to use to describe minimums and maximums, since we're going to see each of them mixed in with all of these different functions moving forward, is what's called a local minimum or a local maximum. And again, it's the same concept as minimum and maximum. It's just simply another way to describe the low point of the graph and the high point of the graph before the graphs continue to either positive or negative infinity. So those are some keywords we're going to come across here in this unit. And again, we're going to use our graphing calculator to plug some stuff in and learn how to find these using the calculator. So in the next part of this here, before we get to the calculator, we can identify some basic turning points, these local minimums and maximums and all that stuff without the calculator necessarily. We're going to do some estimating of this here before we actually punch the functions in ourselves. So a couple of key points that necessarily you don't need to remember, but there's some things, again, that help explain what's happening in the graph. So the first bullet point, if the function has a degree of n, there are at most n minus 1 turning points. What that means in layman's terms, if you have something like a function that has x cubed, that means it can only turn 2 times. Because it has a degree of 3, it will only turn at most twice. If you had a function that was like x to the 4th, so that's a degree of 4, it would only turn at most 3 times. Now, that also correlates in some respect with the amount of zeros that you can get from the graph. So a couple of bullet points here that will kind of help you, again, determine how things move on the graph. If you have a zero that, so aka crosses the x-axis, if that technically occurs in your problem an even number of times, that zero will occur at a turning point, aka the graph will bounce off the x-axis. If it occurs an odd number of times, then the graph will cross through the x-axis and continue on to some other points. Most of your graphs will have zeros that repeat an odd number of times, aka you only get them to come up once. There are a few functions you'll see, and we'll see one in this video here, where it technically repeats an even number of times, and you'll see at that zero, the graph does bounce. But before we really get too much into that, let's be able to identify where these occur on a graph and be able to pull some and estimate some basic points here. So on the left side here, I just give you a really generic function that turns and twists all over the place here. Let's identify a couple of key parts to it. So what I have here in red are the local maxes. Now, the one on the left is truly the actual maximum of the graph because it is the highest point before obviously going all the way up to positive infinity. But both of those red dots there that I've labeled, those are local maximums at those parts of the graph because they top out in those areas. Conversely, the two purple dots that I've labeled are local minimums. Now, they're both like roughly the same spot. If we eyeball it really closely, I think the one on the left in purple is technically a little lower, so that would be your true minimum. But again, you have two places where the graph bottoms out, so those we would consider to be local minimums. Your zeros, aka your x-intercepts, are where all of those green x's are. And actually, it looks like I missed one here on the far left side as well. My apologies for that, but it is an x-intercept. So anywhere the graph crosses the x-axis, that is a zero, aka an x-intercept. That has not changed. So being able to identify those parts, again, will help you structure the graph. It'll help you plot your points and identify some key information there. So the graph on the right here, a little bit more formalized here. We've got points on a coordinate plane here. So we're just going to identify the zeros, the local maxes, and the local mins. So I look at this graph here. Again, my zeros are going to occur anywhere the graph touches or crosses the x-axis. So I see three different zeros. I see zeros at -3, 0, 0, 0, and 4, 0. And if you look closely here, you can see I've highlighted those in green. Now I will say -3, 0, and 4, 0, they only technically occur once in the function because the graph just goes straight through them. That 0, 0, it seems to bounce at that point. So since it bounces, that would likely imply that it would occur possibly twice or more, or another even amount of times within the function as well. The other two things we're going to identify again are the maximums and the minimums. So again, the local maximums are going to be any place where you see the graph top out. So I've highlighted those in red. And again, we're just estimating here. -2, 3, and 3, 7, those will be your local maxes. Your local min, we're looking for any place on the graph where it bottoms out. I only see that in one spot, and again, it's a repeating point with one of the zeros here. And that can happen sometimes where a zero can act as a max or a min. That's totally fine. Just have to go with whatever the graph gives you. 0, 0 is where the graph bottoms out, though, and that would be a local minimum as well. Now, sometimes it's appropriate to estimate these, but again, I'm going to show you on your graphing calculator how we can get more exact answers because, as you can see, with more complicated functions, there's going to be more complicated points. So it's not always going to be at a grid point. It's not always at a lattice point. It's not going to be always as easy to grab as a 0, 0 or a 3, 7 or something like that. So we are going to go through on the calculator here in just a moment how to find those. So in your notes, and you'll find this here as you can see on the next screen, to use your graphing calculator, there's a series of several steps. Now, a lot of these we've already gone through in terms of how to enter into the equation, get your table of values, pull up the graph. None of that stuff is going to change. The new part that I'm going to teach you here today is that step 5, which is how to find any zero, how to find a minimum, and how to find a maximum. These are all in the table, are all going to be in the same spot and take roughly the same steps to get to in the calculator, but you do have to know which is which. One of the things, and you see the note in bold at the bottom here on the left side, some things you're still going to have to verify using algebra. So while the graphing calculator is going to be great for some of these different things that we're doing here, and I certainly want you to use it to your advantage, there are going to be some instances where you have to use algebra to verify that you understand the math that's occurring and you're not just randomly pushing buttons. So don't always rely on your calculator, but certainly use it to help yourself out. So I'm going to go through these instructions step by step with the two problems that follow this slide here. And again, if you're following along in your notes, it's at the bottom of this page. So feel free to refer back to this anytime, but this is a pretty well spelled out step by step as to how to find all the information that you're going to need. So let's go ahead, take a look at the two examples at the bottom. So we're going to look at the first function here, and we're going to go we're going to plot the points, get our table of values, all that good stuff. Then we're going to use our calculator to find the zeros, the maxes, the mins. Now, here's our function here. So once again, to type in a function, y equals is the button you hit. So that's the screen that's been flickering here for the last few minutes. We're going to go ahead and type in our entire function that's here. So again, type it as you see it. So again, forgive my speed on typing some of this stuff in. I am using this on my laptop, so it will take me a second here. But here's your function. 0.25, x plus 2, x minus 1, x minus 3, all in parentheses. So I'm going to go ahead and graph it. Now, you'll notice in this graph here, just to point out a couple observations here, it turns twice. makes sense because if I look at this problem here, there are 3 x's in it. So technically, if I were to mush this all together, this would be an x to the third. Based on a point that I brought up before, graphs that are x to the third at most are going to turn 2 times. So that kind of correlates here. And we can kind of see where all the points are going to lie. Now, the one thing about these graphs, so with the parabolas that we were doing in the last chapter, we only worried about getting a handful. You had your vertex and a couple pairs beyond it, and that was enough. My recommendation, so that these sketches are as accurate as possible, I would find every single order pair you can possibly plot. So it might seem a little tedious, but because these graphs are going to turn more than what we were doing in the previous unit, we want to make sure to have an accurate sketch. So once again, to get our table, we go second graph. I want to pull every order pair that's going to fit. So if I look at my table here, -3, -6 seems to be the first one that'll fit, all the way through 4, 4.5. All of those points seem to lie within the table itself. So again, you don't always necessarily have to jot down the table, but again, that is a good reference here. I'm just pulling this straight from the calculator, and again, I'm just pulling all the points that would fit on my typical 10 by 10 grid. So plot all your points. Okay, and again, you can use your graph to match up and say, okay, does this match my picture? And that looks pretty good. Okay, probably means I plotted all my stuff in the correct spot. So now we're going to go ahead and use the calculator to figure out our zeros, our maximums, our minimums. Now, I will say the zeros, based on the way these problems are set up, the zeros you can actually find pretty quickly without using the calculator. I'm going to go ahead and explain how you get them anyway. Excuse me. But if I look at the graph and kind of just look at where they cross the x-axis, kind of looks pretty obvious here. It looks like it crosses a -2, 0, 1, 0, and 3, 0. If I look at my sets of parentheses here, it's kind of basically modeled off of intercept form. If I take each of those sets of parentheses, the x plus 2, the x minus 1, the x minus 3, and set them equal to 0, I would get the same values. Okay. Now, I'm going to show you, using the graphing calculator, how you can confirm that these values are indeed correct. So here's how you confirm your zeros. We would go to second, trace. What second and trace does, you can see in blue, it brings up the word calculate. This menu is what you're going to go to a lot for this lesson to find zeros, minimums, maximums. Okay, so if I want to find a 0, I hit second and trace, bring up this menu. The second option is 0, so I want to make sure to scroll to the second option and hit enter. Now, on your screen, you'll see a flashing cursor, and it's going to ask the question left bound. So let's say I want to confirm, just because it's already centered up here, I want to confirm that 1, 0. So the one where my mouse is at, I want to confirm that this is actually 1, 0. Since it says left bound, I just need to make sure my cursor is anywhere to the left of this, okay? So it can be really close to the left, it can be far away to the left, it doesn't really matter. It just needs to be to the left of it. So since I'm already to the left of it, I'm going to hit enter. Then it's going to ask right bound. You're going to want to scroll a little bit. You want to get anywhere to the right of that 0. So my cursor is now on the right side. Hit enter. You'll see a couple of arrows that kind of point in at each other. Okay, and then it's going to ask for a guess. Don't worry about guessing it. Just hit enter again. And it's going to zoom in, and it's going to have your 0 listed out. X is 1, Y is 0, so the point 1, 0. I can use that to test out the rest of them if I wanted to. So if I wanted to figure out, again, if this was 3, 0 right here, make sure that was actually correct. Go back to second trace, second option. So again, I want to be on the left side of this point here. So again, anywhere on the left is fine. Then I want to be anywhere on the right. Okay. When it says guess, again, we don't guess. We just hit enter. And once again, it will zoom into where the 0 will be, 3, 0. And then I could obviously go backwards and test on my calculator for -2, 0, but I promise you it is correct in this case. So that's how you can use your calculator to verify if the zeros you got are actually correct. We're going to use this menu to figure out minimums and maximums in a second. I do want to point out one little detail. Sometimes the calculators get goofy, and they'll weirdly round things because of just the way that they process the numbers. If you ever get a number, let's say you're finding a zero or you're finding even a min or a maximum, and maybe the y value or even the x value comes up as some like weird decimal with an e. E in the calculator refers to some old scientific notation that you probably learned back in like elementary school or maybe middle school. They make a big emphasis on it, and then it kind of goes away. If they rounds it weirdly, okay, using scientific notation, it is going to round off to zero. Okay, it's just sometimes the calculators can only process so much. There might also be instances where maybe you get something like a 2.9999999 or something like that. In those instances, it is getting towards that whole number. It's just that, again, the calculator can sometimes processes things a little weirdly. So don't always just rely on here's the number that's there. Use some common sense in terms of how to interpret that so you can write the correct answer. Now, moving forward here, let's talk about local max and local min. So my local maximum is occurring right here. Now, if I look at my graph, we can probably estimate where it's at. But I want a more exact answer. And you'll see with these, this is where the calculator will really come in handy. To find this max, so again, right where my mouse is pointing, what I want to do is go back to that calculate menu. So second trace. If I want a maximum, that is the fourth option. So I'll hit enter. I'm going to do the same thing I did with the zero. So I want to get to the left side. So this will take me a second here, a bunch of button clicks here. I want to get to the left side of where I think my maximum is. And then I want to get to the right side of where my maximum is. So again, make sure you hit enter after each of those. Hit enter after the word guess pops up. And boom, there's your maximum. So you'll notice it's not at a nice grid point, okay? Those decimals are not incorrect. That is the true maximum of the graph. So when you write out your final answer for these, rounding to 2 decimal places is fine. 2 or 3, whatever you feel like here, but at least 2. And that's what I'll typically round to. I don't need all the crazy numbers after the decimal here, but give me at least a couple of them and round appropriately. So that maximum is not quite, if you look at your graph, it looks like it's at roughly -1, 2, and it's certainly close to that. But truly, your maximum is at something around -0.79, 2.05. To find your local minimum, you're going to do the same thing. So here's your minimum on the right side, so right where my mouse is. We're going to go to second trace. Option 3 is minimum. So again, I need to be anywhere on the left side here. So I always like to scroll them closer together, but again, it doesn't matter. As long as you're on the left side when it asks for the left bound, and then make sure you're on the right side for the right bound. Hit enter. You can see your minimum, roughly 2.12, comma, -1.02. So again, if I'm eyeballing from the graph, a good estimate would be 2, -1. And again, that's really close. But if we want to be a little bit more accurate, we're going to let the calculator do the work for us. That's how you can use your calculator to not only graph and plot the points, but to also find all this other information that's being presented. So I'm going to walk through the second example just so you can see all the information one more time here. We'll do it with a little bit more speed, but we get kind of the same gist here. So let's go ahead and type in the second function. So we've got a fraction here, so I'm going to use my fun little fraction menu, alpha y equals enter for those of you that have it. And again, if you don't have that option for the little fraction menu, again, just type your fraction in a set of parentheses. So we have 1/6 times x plus 3 times x minus 2 squared. Now, the fact that we have an x minus 2 squared means it technically occurs twice. That'll mean that one of our zeros, one of our intercepts, will actually be a turning point and will be bounce off the axis as well. So let's go ahead and graph it. Pretty similar to the last problem. Nothing fancy there, except again, you'll notice where the graph kind of bounces, it looks like it bounces off the x-intercept, or the x-axis, I should say, which kind of makes sense given that one of our factors here is being squared. Go ahead and pull our table of values so we can plot. Now again, I want to pull points that actually fit. So the first one that's going to fit is -4, 6, all the way to 4, 14 thirds. If you have these as fractions and you don't like that, one quick thing you can do is you can go to mode and there's going to be an option that says answers. If you turn the answers option to DEC and hit enter, you can go back to your table, and now you have decimals. So I know some of you like decimals way more than fractions, and I would agree it makes it a lot easier to plot your points. You can go ahead and fix it that way. So here's my table of values. We'll go ahead and plot everything here once it comes up on my screen. So here's my graph of my cubic function here. Again, I look at my graph. Points match roughly where everything should be plotted. Life is good. Now, let's go find their zeros. So once again, finding the zeros should be easier because of the fact that it's an intercept form. You take each of the little factors here, the x plus 3 and the x minus 2 squared, and set them equal to 0. You should technically only have two zeros in this case, negative 3 comma 0 and 2 comma 0. Now technically, that 2 comma 0 occurs twice because that factor, that x minus 2, is squared. Technically, it occurs twice, which is why it bounces at that point on the graph rather than goes straight through the point. Something to keep in mind there, you don't need to write it twice because that's not super necessary there, but just so you're aware, mathematically, 2 comma 0 is a double root, it's a double solution. Again, if you want to verify that on the graphing calculator, second trace, option 2 for 0, and again, I need to be on the left side and on the right side of whatever 0 I'm trying to find. So if I'm trying to verify this guy right here where my mouse is, hit enter. I don't know why I did that. Let's go ahead and go back to our graph. Let's try that one more time. Again, we'll make sure we're on the left side. And we'll make sure we're on the right side. Hit enter. Not quite sure why it's doing it for that one, and admittedly, since this is just kind of a live video here, we'll have to figure that out separately. It should do that with no problem. I'm not really sure what the glitch is with that, but I can assure you, because again, the fact that it's an intercept form, 2 comma 0 is indeed one of the zeros. The other one is negative 3 0. I can assure you those are good. Let's hope that we don't have an issue with that with our maxes and mins. So to find our local max, so here's our local max right over here somewhere. Let's go back to second and trace. So let's go to, again, select maximum if you're trying to find a max. So again, I want to be on the left side of it. So go ahead and scroll. Then I want to be on the right side of it. Hit enter. There we go. Okay, that calculated well. That's good. So you get your max that pops up, negative 1.3333, so on and so forth. So it looks like negative 1 1/3, comma 3.09. Do the same thing to find the local minimum. So again, here's my minimum of my function right here. Now again, contextually speaking, if it bounced there, the minimum should be the same as that 2 comma 0 that we found before. Let's see if our calculator actually verifies this though the right way. So second and trace, find our minimum. So again, you want to be on the left side of the minimum. And again, I'm more showing this just because that I want to make sure, again, you see the button presses one more time. Be on the right side of it, and let's hit enter. Oh, that seemed to work out fine. Now, this kind of alludes to what I was talking about before, where sometimes the calculator likes to do funky computation here. So you notice you get 2.0002 and y equals 3.445 e negative 12. Here's what's really happening. The x value is 2. It's just that the calculator doesn't like to compute every number sometimes. It doesn't process it well enough. The y value, 3.445 e to the negative 12, is the same thing as 3.445 times 10 to the negative 12, which is this incredibly tiny decimal that truly means 0. So I promise in these instances, you can do rounding. If you see something with an e, it's coming out to 0. I'll tell you that right now. It's a very tiny decimal that's right approaching 0. If you have a decimal that comes out where it's a bunch of 0.000s or 0.99999, you can round it as you typically would. But your minimum truly is, in this case, 2 comma 0. So that's how we use our graphing calculator to further analyze some of these polynomial functions. little bit longer of a video here, but again, want to get you acclimated with the calculator so that, again, you can use this to better find these different values. Let me know if you have any questions, and thanks for watching.